So today's lecture we will be discussing what's discussed in the week 6 class, that is how to solve or optimize the function subject to inequality constraints. So what we do is we use something called Kuhn-Tucker conditions for solving those kind of problems. So the derivation for these conditions are very nicely explained in the, I think, lectures. So I'll be just stating those conditions for two type of inequalities, and then we will be solving three problems. One is conceptual, and two kind of number crunching problems, so that we can solidify our concepts. Okay, so let me start. So let's say we have a function. So okay, my screen is visible, right?
Visible, sir.
Okay. So we have a function fx that we want to minimize, and it has, let's say, m number of constraints, and that are, like, let's say, gj x less than equal to 0, where j can vary from 0, not 0, actually j will vary from 1 to m. And the x actually here means that this function is a function for of n variables, x1, x2, so x. So in this particular case, what are the necessary conditions for uh, optimization? So they are, so if you want to tell Mr. Pankaj, what do you think they are? Okay, so let me write, and then you can tell whether I have done some mistake or not. Okay, so
Okay, sir.
let me let me highlight this. We have the constraint less than equal to 0. So we will have first, our basic variables, that is x1 to xn, the differential of the function with these variables, and the constraints. And what did we call these lambdas, Mr. Pankaj, if you can tell me?
Not idea, sir.
Okay, so do you remember this thing? In equality constraint, we had when we had a constraint, then we added those constraint by multiplying with the factor and made a new function.
Yes, sir.
So do you know the name of this function that we made new function? So it was we called it Lagrange function, right? Is that correct? So we called them Lagrange functions, and these were Lagrange multipliers. So they are the same in this also, in inequality also. While deriving this Kuhn-Tucker conditions, what we do is, first we write this function. First we transform this function by combining the uh, function and the inequalities, the function and the inequalities, and then we make a Lagrange function. This will be fx plus lambda j. So we actually add all these inequalities. So we have m inequalities. So we will have m inequality constraints. So we should have m Lagrange multipliers. So then we do the same thing. So you can check in the video, search video, that we differentiate this particular thing with lambda, with x, and then with some other variables, and then we put that to 0. That's how we get our these conditions. Okay, so let me not go into the detail of the derivation. Let me just state the conditions. So this is the condition that the first differential of this function f plus the lambda and the first differential of this constraints should be 0. Then the second condition, lambda j and gj is equal to 0. So the constraints multiplied by their Lagrange multiplier each has to be individually equal to 0, like this. So this is what meant by this. And then our normal constraint itself, that is that gjx should less than be 0. So that's what we have. This is also one of the condition. And one important thing one important thing is the lambda j is that these Lagrange multipliers has to be greater than 0. So these are the Kuhn-Tucker conditions when we have inequality less than equal to inequality constraints with us. So you can note this down. And yeah, so this is also minimization. Okay, and one important thing. So if you remember this, then it is very easy to like to remember what will be the constraints or what will be the condition when we have the same function minimization of fx. Sorry, I don't know. Minimize f of x when the inequality constraints are greater than equal to 0. So previously we had less than equal to 0. When we have equal greater than equal to 0, then what you have to do is simply reverse this sign and this sign. So let me write it more cleanly. So first we have our differentials with the normal variables that we have. That will be 0. Then we have our all the constraints multiplied by their Lagrangian multiplier will be 0. And then we have this constraint. So we have this, all the constraints should be greater than equal to 0, and lambda j will be less than equal to 0. So you can kind of think or visualize that if the constraint are less than equal to 0, then your Lagrange multiplier will be greater than equal to 0, and if the constraint are greater than equal to 0, then your Lagrange multiplier will be less than equal to 0 for a minimization of fx. So these things are important for this Kuhn-Tucker, Kuhn-Tucker conditions. The signs are very important. So I'll give you guys, let's say, 1 minute to note it down. If you have noted it down, Pankaj, you want to say something?
No, sir. No.
Okay. So you guys can actually note down these things. So this is for greater than equal to 0, and this is for less than equal to 0. Can I move forward?
Yes, sir.
Okay. So now that we have no, we have gone through this, let me ask you one this that whether both of you have you gone through the video, like the NPTEL video?
So,
Okay, very good. Then the next question should be very easy. So let me go to the question that I made. Yeah. So this is the question. Consider, let's say, let me write it like this. Let's say I have a function f of x, where x is like x1, x2, x3, and then it has two constraints. And they may be equality constraints, they may be inequality constraints, we don't know. Okay, this is the true constraint. Now if I have given you guys that at optima, at point of optimization, the gradient, that means dj x by dx, so for all the things, for this one constraint is 1 2 3, and for the other constraint it is 5 7 8, then which one of these will be the gradient of this function with respect to these points, the function points. So it is a function of x, x1, x2, x3. So what do you think will be the gradient of this? So do you guys have like any idea how to approach this problem? This is not a standard problem. I just saw one. Uh, I also watched the videos, so I saw this point interesting, and I thought you should remember this. That's why I framed this question. So can you guys note this down so that I can move to the uh, original notepad, because I will be asking these options, and you will have to tell me. Have you guys noted it down?
Yes, sir.
Okay, so I'll be shifting to the class screen. Okay, so this is the first question for today, kind of conceptual question, that if, okay, at point of optima, if I have del of g1 as 1 2 3, and del of g2, what was the del of g2? Can you tell me, Jasurya? Okay, let me, I think it is 4 7 or 4 7 8. Let's take this.
579.
579. 579. Okay, good.
578, I guess.
578. So 5.
578.
Okay. So yeah. So if these are the gradients of these constraints at the point of optima, then what will be the gradient of the function? That was my questions. And what were the options? Okay, let's leave the options. Oh no, we need the options, right? Okay, we need the options. Can you tell me the options? Okay, let's leave the options. Let's solve the problem like this. So what do you think is the concept that we are going to use? Any idea? Okay, so it is basically depends on one of the condition of the Kuhn-Tucker conditions. So this condition, if you look carefully, can you do you remember one line that sir said for these conditions?
Yes, sir.
Okay, so can you tell me, Jasurya, what was the line?
So it was something like the gradient of the function can the negative of the gradient of the function can be expressed as the linear sum of the gradient of the these functions.
Perfect. That's the point that I wanted to reinforce. So, if something, let's say, if y, or let's say, if a vector v1 is a linear combination of two vectors, then what will be, and this is a vector like a transpose vector x, y, z, like this. So, what will be the determinant of a matrix that hosts these three vectors? What do you guys think? So, kind of two, three concepts are getting into this thing. What do you guys think will be the determinant of this matrix, which has x1, y1, z1, x2, y2, z2, x3, y3, z3, where you can actually write x1 as a function of x2, x3, y1 as a, and so on for y1 and sorry, z1. So what do you guys think will be the determinant of this particular matrix? Okay. Uh, so are you guys familiar with the concept of rank in a matrix?
Yes, sir.
Okay. So what does rank signify? Rank signifies. Yeah, tell me.
Like if the rows are multiples of each other or not. Something like that.
Kind of true, but actually the correct definition of a rank will be in a matrix. Let's say a matrix is of the order m cross n. Maybe it's not a square matrix, it's a matrix of order m cross n. Then rank will be the maximum number of independent columns or rows in a matrix. Not maybe not maximum, the number of independent columns or rows in a matrix. So when we have a matrix that is a 3 by 3 matrix, and when we say that in this particular matrix the rank is 2, that means only two of these columns or so rows or columns are independent, and the third one can be written in the form of the other two. Then in that case, when we apply the row echelon transformation, we can actually make this column 0, right?
Yes, sir.
So then in that case, what is the determinant of this matrix?
0.
0. So the coming to back to our original question, what will be the determinant of this matrix if one vector can be expressed as a linear combination of the other two?
0, sir.
0. Okay, so now we have these two vectors that signify the gradient of the constraints at the point of optima. So now let's go back to the options and see which one is going to be the gradient of the particular function at the point of optima. So can you guys tell me which one is going to be the gradient? which one will be the delta?
Is it yes?
Which one?
Option A.
Option A. Okay, so how do you say option A? This is 0.5, this is 2, and this is 1.5. So I actually willingly put the option A looking a little bit, closer to the answer that we want to see, so that we'll miss just that. Linear combination does not have to be strictly a multiple. It can be anything like delta G1 minus delta G2, something like that, or 5 times of this and 4 times of this. What I will suggest you guys is you put it into a matrix and then tell me which one you are getting the determinant as 0. Don't get confused by this. I'm just writing it to explain. It's not 4 delta G1 minus 4 delta G2. Okay, I think it's taking a little too much time. So just subtract these two. So when you subtract the delta G2 with delta G1, you will get 4, 5, 5. And do we have this in our options? We have. Sorry.
Yes.
So this will be the answer. But so I think you guys understood the concept. So that
Yes.
was, yeah. So that was my intention. So let's go on for the other problems. Okay. So question 2 for the day. Okay. Okay. So we have a function f of x is equal to x1 square plus 2x2 square plus 3x3 square, and we want to minimize this function, which is subject to the constraint g1 x is equal to x1 minus x2 minus 2x3 less than equal to 12, and g2 is x1 plus 2x2 minus 3x3 less than is equal to 8. So now I ask you this: what will be the equality sign that should I put here and here? Try to recall. Minimization problem, so nothing fancy about this.
Less than or equal to 0
For which thing?
for the Gj of x.
Correct. And for the lambda?
Lambda j is greater than or equal to 0.
Perfect. So it should not, this one should not be a problem because we are given the constraints. So the optimization, the necessary conditions should not be opposite to the constraint. So it will be same only. So we have g less than equal to 0, and as I said, I like to remember it like the lambda is the enemy of g, so it should be opposite to the g. So let's now try to solve this question. So okay, I will erase this. I'll write it somewhere else so that I have some space. So conditions. Let me write Kuhn-Tucker conditions. That is, so this is we all are familiar with. Then this is also. Then I just ask the things which might be confusing, and you have answered it nicely. So these are the Kuhn-Tucker conditions. Okay. Now let's try to get the equations based on our first condition. So let me write condition 1. Okay, so what will be the differential of, so what will be the this thing for the first variable? Let me write it, and then you can tell me whether I am doing anything wrong or not. So I think it should be 2x1 plus lambda 1 x1 plus lambda, sorry, plus lambda 1 plus lambda 2 is equal to 0. Is this correct? Maybe it will be helpful if we write the Lagrange function first. So I have written this Lagrange function. Can you tell me what is this S1 square and S2 square?
No idea, sir.
Okay, so do you remember, did we do this? In some optimization, we added some things, no? Yeah, in the simplex method, I think. What did we do to remove the inequality?
We added a function.
No, no, that is artificial function that you are saying. But normally when we had minimization problem and this is less than equal to 0, but we want to write this function in the Lagrange function, so we can't have this inequality. So we added a variable and we called it some kind of a slack or something. You remember?
Slack variables.
Yes. So yeah, so Mr. Pankaj correctly stated. So these are just slack variables. You can write them in any matter or any way you want. I just wanted to make sure that we consider them as positive. So I have written here S1 square and S2 square. So because we need to add something here to make it equal to 12, right? Yeah. So now that I have written here the Lagrange function, can you tell me whether my this particular differential of this function with x1 variable is correct or not? Let me write for x2 and x3, then you can together tell me what is the correct one. Hmm. Now you can tell me whether what I have written here is correct or not.
Sir, how these conditions not getting?
Are you not getting how I am writing this?
Yes, sir, yes, sir.
Okay, so till this, are you clear that I am trying to write this here? So these are the Kuhn-Tucker conditions for us, necessary conditions for us to find the point of optima, which is first you have to differentiate this function with respect to a variable, then differentiate the constraints constraints multiplied by their Lagrange multiplier, and then with that same variable, and then equate to 0. So, and how this comes in the optimization condition, when you see the video, I think it will be much clear. That is, we make the Lagrange function. So what I wrote here is our Lagrange function, which is summation of the function, that is this term, sorry, that is this term, and the constraints after removing their inequality sign.
Now clear, clear.
Okay, with
I
the,
got.
okay, so did you also get, okay, so we have a new participant, Sandeep. So you'll have to catch up, Sandeep. Or maybe you will understand along the way. So when we differentiate this Lagrange function with respective x1, x2, x3, so it should be this one. So now you tell me whether I have differentiated them correctly or not.
Correctly.
Okay, good. So this is the condition 1. What is condition 2? Condition 2 is the inequality sign multiplied with their respective Lagrange multiplier will be 0. So that means it is nothing but, let me write here, condition 2. Condition 2 states that the inequality, that is first inequality, okay, let me, first inequality, that is x1 minus x2 minus 2x3 minus 12, multiplied with their Lagrange multiplier, that is lambda 1, will be 0, and the second one, so what we do is, when we are writing this, we don't go and consider this slack variable, because this condition, it's actually to check whether which constraint is active or not. So if the active or not means whether this is the constraint that is actually going to uh, act in, which is going to play a role, critical role in the optimization or not. So if the lambda is 0, then that means whatever this constraint value, we don't care, it is not going to affect the Lagrange function or something. So yeah, so this constraint particularly is used to check which particular inequality is active or not. So if you want to go into the detail, you can follow the video, the NPTEL video that shares here, or if you just want to know the gist, this is the gist to check the whether the constraint is active or not. So is this correct? No, it feels correct. So let's move on ahead and write the other two constraints, conditions. Condition 3. Condition 3 was each constraint should be followed. So these are the constraints that were subjected. I just move the 12 and 8 to the left hand side, and that will be less than 0. Then we have condition 4. So as I said, in the minimization case, no need to worry about these this lambda sign. You just remember that whatever the sign of G, lambda will be opposite to that. So our lambda 1 and lambda 2 will be greater than 0. Is this correct?
Yes, sir.
Okay, so now that we have these things, these set of equations in our arsenal, let's call them equation 1, equation 2, equation 3, 4, 5, and these are the inequality things. We are not going to be using these to solve. So let's remain till 5. So now what we will do is we will use these 5 equations to get the value of x1, x2, x3 that satisfies these constraints. So to do that, we will choose one of these two equations, number 4 and 5. So for this to be true, lambda 1 into the constraint is equal to 0, lambda 2 into the constraint is equal to 0. There will be two cases. Case 1, let's say case 1 is lambda 1 is equal to 0. So this satisfies this, so we can assume that. And in that case, this particular constraint is not equal to 0. Okay, so when we have lambda 1 is equal to 0, let's try to solve for x1, x2, x3 or lambda using the remaining equations. So we have 1, 2, 3 and 5, and we have x1, x2, x3 and lambda 2. So we have 4 variables, 4 equations. Let's try to solve. So from these equations, that is equation number 1, 2, 3, if we put lambda 1 is equal to 0, what will be the value of x1? So let me write it here. I will shift it to shift it below after we have finished this. What will be the value of x1 from, yeah,
Lambda 2 by 2.
I-
Minus lambda by 2 by 2.
correct. Similarly, x2,
Minus minus lambda 2 by 2.
correct. So don't be afraid if you're thinking it is same, if something is wrong. It might be same also. So what about x3 then? So I think you get the gist. So x3 will be lambda 2 by 2 without the negative sign. So by looking at it, so it was an easy expression. We were able to solve this. Now we have x1, x2, x3 in terms of lambda 1, lambda 2 and lambda 2. So now what we do is we put this value, or more nicer term, substitute this in equation number 5. So let's do that. So we have equation 5. You can see it is nothing but the second Lagrange multiplier, that is lambda 2, into the second constraint, that is and equal to 0. So when we put this into that constraint, we have lambda 2 into x1 plus 2x2 minus 3x3 minus 8 equal to 0. Now let's put the values. Minus lambda 2 by 2 plus 2 minus lambda 2 by 2 minus 3 lambda 2 by 2 minus 8 is equal to 0. Is this correct? And can anyone tell me what is the simplified form of this? So I will also do. I hope you will also tell me if I am doing something wrong.
Minus 3 lambda minus 8.
Perfect. So this is the uh, simplified form. So for this to be true, lambda 2 can be either 0 or lambda 2 can be minus 8 by 3, correct?
Correct, sir. Correct.
But here's the thing, when we wrote our conditions, we wrote an important point, that is all lambdas will be greater than 0, and this particular thing doesn't satisfy. Only one of these two values satisfy. So we will ignore this and we will calculate the value of x1, x2, x3 from the lambda 2 is equal to 0. So when we have that, our x1 will be minus lambda 2 by 2, that is 0, x2 will be same 0, and x3 will be 0. So we get our x as the solution vector as 0, 0, 0. Now let's see whether these values satisfy the constraint. So we already know, we assumed lambda 1 to be 0 and lambda 2 comes out to be 0. So they both are satisfying this inequality. And we got these values by solving these equations 1, 2, 3 and 4 and 5. So they will definitely satisfy these equations. Let's see whether they satisfy these inequalities or not. So what do you think? Do they satisfy this inequality? So we have to discuss another problem. So I think you should tell me fast. Just put 0 and see whether inequality is correct or not. Okay, so when we put 0, 0, 0, 0 minus 2 into 0 minus 12, is it less than equal to 0? So basically minus 12 is less than equal to 0. This is correct or not?
Minus 12 is less than 0.
Yes. So what do you think? This is correct or not?
That's correct.
It is correct. Perfect. So when we substitute for this equation also, we will get minus 8 less than equal to 0. So if you are confused, maybe I should say this if one condition in this less than equal to or greater than equal to is satisfied, then we consider that this particular inequality is true. So 4 is greater than equal to 0 is true because 4 is greater than 0, not equal to 0, but one of these is satisfied. So yeah, in this case the inequality is satisfied. Okay, but how do we know this is the solution? Because we have only explored one of the cases. We have not explored the other possibility. So we will first explore that, and we will check which one is going to give the minimum value of f, and we'll consider that, because what these conditions are, you have to remember, Kuhn-Tucker conditions are not sufficient conditions, they are necessary conditions. They can be sufficient when the function is convex in case of minimization, but naturally in their nature they are not sufficient conditions, they are only necessary conditions. So 2 points can follow these necessary conditions, but we have to select the point which is going to give the minimum value of f. So what was the case 2? Let's see. So case 1 we assumed lambda 1 is equal to 0. Case 2 will be this inequality is equal to 0. So let me take this inequality from here and Okay, I'm not able to paste it, so let me just write it then. X1 minus x2 minus 2x3 minus 12, x1 minus x2 minus 2x3 minus 12 is equal to 0. So this is our second condition. So we will use this and the equations 1, 2, 3 and 5 to get the to see whether our from this case we can get some value of x1 or x1, x2, x3 that satisfies all the inequalities. So when this is equal to 0, let's write the value of x1, x2, x3 in terms of lambdas. So if this doesn't work, let me try to move it. Yeah, let me move this itself. So we have this. Okay, so now we can write x1 as minus lambda 1 plus lambda 2 by 2, x2 as lambda 1 minus 2 lambda 2 by 4, x3 as 2 lambda 1 plus 3 lambda 2 by 6. So is this correct? What do you guys say?
Yes, sir.
Okay, now let's put these values into this expression to get the to make an equation in lambda 1 and lambda 2. Okay, so it's a pretty complicated looking equation. Let's try to simplify this. So I will simplify. You guys tell me whether I have done it correctly or not. What I will do is I will take LCM of 12. Sorry. So 6, 9, 6, 3, 9, 17. Then this cancels. So is this correct simplification?
Yes, sir.
Okay. So my one question to you guys. Let me move light it a little nicely. Sorry. So what do you think? Is what does this equation? So typically to solve for lambda 1, lambda 2, we need another expression, which we can actually get when we substitute x1, x2, x3 in equation number 5, and then we simplify it. We can get another equation in lambda 1, lambda 2, lambda 3. Sorry, lambda 1, lambda 2, and then we substitute one of these lambdas from this. Let's say we write lambda 1 is equal to minus 144 minus 12 lambda 2 by 17, and we can put it into that equation, and we can solve for lambda 1 and lambda 2. But instead of doing all those things, if we look at it carefully, this particular equation, we can actually avoid doing that. And why do you guys think we can do that? I will give you a hint. Can the sum of two positive numbers be negative?
Never.
No, right? And
Yes, sir.
what do we see here?
Yes, sir.
So that's what we see here, right? So we have set our constraints that lambda 1 is greater than 0, lambda 2 is greater than 0, and this particular case that we assumed that this constraint is 0, it is giving us lambda 1 plus lambda 2 with some positive multiplication is actually negative. So that means if we are going to solve this particular equation, we are going to get one of the lambdas as less than 0. So we don't even need to solve this. Just by observation, we can write here, just by observation, we can say that this condition or case doesn't satisfy the inequality conditions. So that means we have exhausted our cases. We had two cases, case 1 and case 2. Case 1 gave us one good answer, case 2 did not give us any good answer. So the correct answer would be, since we have only one answer, will be this. So this is the point of optima. Now if you why I have a question. So before that, do you guys have any question in this? If you don't have, then
No doubt.
I have a question then. So it is good that you don't have doubt. Now I have a question. We made the case 1 lambda 1 is equal to 0 and case 2 this inequality is equal to 0. Why don't we do a case 3 that is, let me write here, this equal to 0 and case 4 this equal to 0. Why do you think we don't do this? If you think we should do this, tell me if you think we should do this. Okay, no problem. So the answer is we don't do this. And there is a very good reason for that. The reason is when we considered lambda 1 equal to 0, then what are all the equations we used for solving this? We used equation 1, 2, 3, and one more equation, right?
Right.
So that equation was equation number 5. So we already have incorporated this equation in our case 1, and case 2 we we could have incorporated and solved for lambda 1 lambda 2, but we found out that there is no need to solve. But the logic is we are already using this equation without making any assumptions. So the behavior or the answer that we would get by solving this is already incorporated into our case 1 and case 2. So we don't need to go for any further assumptions. And the same way, if let's say you want to say no, our my case 1 will be lambda 2 is equal to 0 and case 2 will be this particular inequality equal to 0, then in the same way we will use equation 1, 2, 3, and 4 to solve this particular x1, x2, x3 and check the inequalities. And while doing that, we have already used this particular equation, and so that's why we don't need to again go for case 3 and case 4 where lambda 1 is 0 or this but gx1 is 0. Is that clear?
Clear, sir.
Okay, very good. So we have only 3 minutes. So I think I have explained the nature how to solve this. let me give write one more equation, and I will ask you what will be the constraint or what are the conditions. So I will not say anything. You only have to tell me what will be the sign of equality and inequality in the equation that I am going to write here. Question 3 is minimize f of x, where f of x is x1 square plus x2 square plus 60x1, which is subject to constraints g1, x1 minus 80 is greater than equal to 0, and g2, x1 plus x2 minus 120 greater than equal to 0. So the normal uh, the normal condition out of the four conditions that are, I will write them, that is this thing where we don't have to apply much brain, we can just finish them off, that is this, and it is this. Now I want to know is what should I write here and what should I write here.
In first one, greater than or equal to 0, and second one, less than or equal to 0.
Perfect.
So, in
Yes.
last question, slack variable use is not clear. Why that has been written over there?
Okay,
Slack
so
variable is two.
yeah. So while in the final conditions we don't see the slack variables, but when you are writing this Lagrange function, so let's say you have, let's take this one itself. When you are writing a Lagrange function for this particular function and the constraints, you have to combine them, right? You have to combine these two. Now it is a rule that you cannot combine something which has an inequality in it. So what we say is, let's say x1 was some value and it satisfied this constraint. So let's say it is 10. So in the end, x1 was x1 minus 80 is greater than 0, and that the difference between this and 0 was, let's say, 10. So means x1 is 90, and x1 plus x2 is minus 120 is greater than 0. Let's say x2 was 20, or not 20, x2 was 30. So that means the difference here was 0. So so when we are initially when we are trying to write this into a Lagrange function, we should actually write like this: fx plus lambda 1 x1 minus 80 plus, oh sorry, minus 10 plus lambda 2 x1 plus x2 minus 120 and plus 0 is equal to this Lagrange function. But since we don't know that what value we should add or what value we should subtract to remove this inequality, what we do is we replace it with a slack variable, the value of which we have to get while we are getting the optimal conditions. We can get, or we don't need these values, but these values need to be there for this inequality to be added to this particular function, because you cannot add this, right? If you have a function, let's say x1 plus y is equal to, or minus 4 is equal to 0, can you solve this particular equation? Can you just see this: x1 plus x4 minus x1 plus y minus 4 is equal to 0, and x plus 3y is less than equal to 0. Can you solve these two for one value of x and y, 1 point?
No, sir.
We will get a range, right?
Yes, sir.
We'll get a region. So to get 1 point of optima, what we do is we add one more condition. Let's say it was less than equal to 0. So to make it equal, I add a positive number. Now we have two equations and two variables. Sorry, three equations and uh, sorry, three variables and two equations. But now we can actually solve this. We consider S1 as a variable, and then if we know the value of S1, we can solve this, right?
Okay, okay.
Yes.
So
So
another question.
yeah.
In the lecture, sir has told to know the feasible direction S transpose has been multiplied in the function, both sides, left and right side. S transpose for feasible direction. What is that?
So is it you're talking about uh, lecture the first one or the second one? So in the week there are two lectures, no? The so are you talking about the feasible direction where he's doing the what is that, penalty function or something else?
The approximate first lecture, I think.
First lecture, right? Okay, so let me check. I'm not 100% sure what you are saying here. Let me check. Visible direction. Okay, so let S be the feasible direction. Then we can write minus this, and since S is feasible direction, this is less than 0, and this. Okay, I am also not sure about this thing. Maybe I will go through this, and so since we don't need this in solution, I didn't pay much attention to this. Let me get back to you on this maybe next week, or maybe I will put a video on that separately.
Okay, sir. Okay, sir.
Okay. So any other thing? Okay. So if there's no other doubt, then I'll end today's session. Thank you for participation, Mr. Pankaj, Sandeep, and Jaysurya.
Thank you, sir.
Thank you, sir.
Yeah. Thanks.